Okay. Everybody rested and ready for the exam? Good, good. I didn't expect a shake of head. Rested at least. Questions? I've heard you should never say questions. You should say, what are your questions? That's more inviting. So what are your questions?
Can you explain synchronized method?
If there's something that I've explained before that you don't understand, come to my office hours and tell me what you didn't understand. Okay? You use that in the assignment, so I hope you understand to some degree. Okay? Other things? Okay. So last time we were looking at recursion. Okay? And we looked at, there was really stuff I covered in 110, and I noticed a lot of you working at half throttle, and it was all very obvious to you. But it was a prelude. I just wanted to make sure everybody knows recursion before we do the real thing I want to do in this class, which is recursion involving trees. Okay? And you will do recursion with trees a lot in the next course. So I don't have to spend too much time on this, but I do want to say enough about this subject so that you can figure out good software engineering techniques to do recursion, okay, which you will not learn in the other course. So you'll get some practice for the next course, and then you'll also learn some other things. Okay. So we did number-based recursion last time, and we did list-based recursion, and we're now going to do tree-based recursion. And just to, and we're going to make use of the composite design pattern, because the composite design pattern is what enables us to create recursive trees in an efficient fashion. Okay. I say efficient because you can do without it if you just make the leaf node and the non-leaf nodes the same type. Okay, which means the leaf node has space to have children, and you don't use that space. Okay, so that's not very efficient. And so that's the background. And just to remind you what a tree is, we have to go back to our logical and physical structures. And you guys have done a lot of structured types by now. And one of the first, at least graphical structured types we saw was the Cartesian plane. And it was doubly structured. So you had the top level structure, then you had lines, and lines were further decomposed into smaller components. And we said that you can create these structures as the most general type for the structure is a graph, okay? Where any node, any component, any of these boxes can be connected to any box, and there's no constraints on how these edges should go. Okay? And then we said we can constrain that a little bit more. And do you guys remember some constraint? Not a tree, but not an arbitrary graph. We use an acronym for it. DAG. Okay, and it stood for directed acyclic graph. Okay, which meant what? That how was it less general than a regular graph?
There could be multiple paths to a node.
There could be multiple paths to a node. So that's like a graph. But it was not as general as a graph. You couldn't have something. You couldn't have go back, or you couldn't have the technical term for it. Loops. That's a good word for it, but that's not the technical term. Cycle. Okay. And then the most constrained structure was tree, and we have a single path to it. Okay. And when we have trees, we can also talk about subtrees. Okay, so there's a hierarchy now, and then so we have a child node of this, itself root a subtree. Okay, so the tree has a root, and every child of the root is also a root of a subtree. And you can think of a leaf node as being a root of basically as one node. Okay? So this subtree includes its root and its children, and this subtree includes just itself. Okay? So this is what a tree is. We know what a tree is now. We build trees. Okay, we use the composite type. So we can have trees that are recursive or not recursive, and you use the composite design pattern to create recursive trees. Okay, and this was a tree we used in the context of our Cartesian plane, and we saw trees occur a lot of places. And here's another, when we create a toolkit, use a user interface, these widgets or these windows, these form a tree, okay, and we created another tree, okay? And this is a tree that has, as leaf nodes, a text field and a button, and these are enclosed in panels, which are enclosed in split panes, which is enclosed in a frame. Okay, so that's an application of a tree. Okay, so all this stuff we know. So what do we need to know now? What additional stuff do we want to do? Well, let's say we built the tree, okay, and it's all created, and we want to later morph it. Okay, so we created that tree, and we said, now I'd like to color the tree. That means take every component that's here, and by component I mean the English word component, and I also mean by that the swing or AWT term component, where everything that you see displayed here is actually a subclass of component. And this component class has a method called setColor. So we can always call setColor to change its color. Okay? And what I'd like to do is, once I've built this tree, I'd like to go to every component in the tree, or every node in the tree, and paint it some color. That's it. Okay? So we've got a tree, and we want to now traverse it. Okay, and I put traverse in quotes first to just sort of give you an intuitive idea of what this means. And this might mean that, say, after your house has been built, we want to color it. Okay, so you get all these contractors to come later and do things with your house. Okay, and put carpets, do things to it. Okay, and while building, we did not do these actions. So we didn't just sort of build the blue color into it. Okay, we just didn't color at that point, and we said that's for somebody else to do. Okay? And this is going to be important. That one piece of code is going to build the tree, and another piece of code is now going to do things with it. Okay, and we want to make sure that these two programmers or these two pieces are not too intimately connected to each other. Okay? And so you can take a real tree, and you talk about birds visiting the tree, okay, or people fertilizing it, okay. So it's all sort of, you're talking about this happening a lot in the natural, okay. So a natural and man-built world. And so now traverse means we're going to visit or process every node in the tree. That's what it means. Whatever this process means, fertilizing, coloring, whatever. So that's a general thing we're going to look at. Okay. And can you guys see how recursion could be applicable here? So I want to go and visit every node in the tree, and could I somehow use recursion?
Because they all share the one method that color.
Okay, so that's good. That at least they all have this one method, set color. So that is, okay, so how's that tied to recursion? So I want to go and visit every node in the tree. So I want to go and, color every node. And yes, every component does have the color method. But where's the recursion? And remember, recursion is, you're given a big problem. You don't know how to do the whole problem. You can do part of the problem and then say, do it again on a smaller version of my problem. Marie?
Are you thinking of starting at the root or
Okay, so that's one thing. We somehow have to go and traverse the whole tree. And we can start at the root, or I can start at where else? The leaf node. So I have how many roots in a tree?
One.
How many leaves do I have?
Many.
Okay, so then the question becomes, which leaf do I start at, right? That's one question.
Yeah.
You can say I can start at any leaf.
You could have one.
You could have, but in general you'd have more leaves. Okay? So, if you've seen fall, you know a tree has a lot of leaves. Okay? And so, it would be nice. Or it wouldn't be nice. At least at this time of the year, it would be nice if there's only one leaf. So you have many leaves, and so that's the question. And then, you know, when I draw these edges, you see edges going from the parent to the child or the child to the parent. So you have to be able to reach nodes from the parent. Now, you might also have links back. And if you do so, and you display it with the object editor or with the swing toolkit, it'll complain and say, sorry, I've got a cycle, I can't deal with it. Okay? So if you're going to start with the leaves, we don't know which leaf to start with. And we don't even know how to go from a leaf to its parent. We do know that the parent should have links to its child. But the other way around, in a tree, we don't even have these links. Okay? So we have to start from the root. And in here, is there some way you think we can do recursion? Derek?
You can find a method that paints the node itself and then paint on its child node.
Okay.
And we can call that on each of its child. Call it method.
So basically what you're going to do is, we said traverse or visit every node in the tree. Okay, so how do we do this recursion? We traverse node by visiting the node. Okay, and traversing the subtree rooted by each child. That's essentially what you see. Okay, this is just recursion at work, and it's really effective. So we're going to define a method that traverses the entire tree rooted by some node. That's the method we'll do. Okay, so tree is subtree, and it's going to go and say, oh, I've got to do this whole big task. That's just very difficult, so let me go and break it up, and then maybe it becomes a little more tractable. So I'm going to go and visit the node, okay? And that I can do. I can always go and color a tree, color a node. That's easy. We all know how to do it. And then I will do whatever I did to this thing by traversing the tree rooted by each child of the node. I'll do the same process here. Okay? That's the basic idea behind tree-based recursion. Okay? It's like when we did list-based recursion. You know, we would do something with the thing at the head of the list, and then do this, and then go and process the tail of the list, the remaining part. Okay. So tell me now. Here's my thing. I'm going to have a method. I'm just going to do this all the static methods. Okay. I've got a color method that I can always go and set the background of. You know, I can use here. So I can say set background to the color. Okay, which is going to be some constant. And so this is the non-recursive part. Okay, this is my visit method. This is where I process. This is what the real work happens. Okay? And I need to call this method recursively on each node. So I'm going to define some other method which is recursive, color subtree, that's going to somehow call color, and it's going to be given the root component in a subtree. Okay? So that's what we have to do. Okay, we got the general idea. We want to go and look at the nitty-gritty details and see the real code. So tell me, what exactly will this method do now?
So it will set the color of the root node.
Okay, so that's easy. We know that this component, the root is a component, so I can go and just say color component. Okay, now I could go and, okay, so that's one way to do it. Okay, and then what? So that's my non-recursive step. Well, okay, that's my sort of.
So first then the second step called color subtree on each of it.
So call color subtree on each of the children.
Yeah.
And how do I know what the children of this component are?
You need to have a method, probably.
Okay, so you need to have a method that somehow gives you the components. And any of you guys use that method in your AWT swing code? No? Okay, yeah.
The method to get the components
Yeah.
of the container.
Oh, you can always look it up.
Yeah, I just looked it up.
Yeah.
Get
That,
components.
when I ask questions, and you know, Google is this great thing, right? It says you don't have to think ever. You know, and when I go out to lunch with friends, you know, they like the fact that they have Google because I can't give them wild theories they can't verify. So, but it's no fun any longer. You can't give wild theories any longer. So yeah, you can always look it up. But and you know, people actually have thought of this as really a bad thing, that people aren't thinking about why things are the way they are. They just say, Google, tell me what's the right answer, you know? And so it's a little too easy. It's nice to have that answer after you've thought a little bit. But if you notice, you guys, when you build the tree, you could go and add children to a component. And you can't add children to a vanilla component. You can add children to a special type of component called it's a composite object, and it's called, what would the English word be? Or whatever you, container. Okay? So what we're going to do is we're going to go and check if the component is a container. If it is a container, we're going to go and find its children. Otherwise, we're going to just go and return. Okay? So that's the code. We're going to color the component. And if it's not an instance of container, we're done. Okay? Otherwise, we're going to cast it as a container, find its components, go through every component, and call color subtree of it. Okay? Okay? Yeah.
If we didn't want to check to see if the component was included in the container, we could figure out otherwise the system.
So your question is, what if we didn't want to check? Okay?
Yeah. Well, I want to know if the try-catch would be more efficient.
Would a try-catch be more efficient? So we haven't talked about try-catches in this class.
Yeah.
So, you know, we are doing newspeak. We don't talk about terms we haven't learned here. For those of you who haven't read Brave New World, newspeak was the language that you were... Is it Brave New World or was it 1984? 1984, I'm sorry. I read them both at the same time. So, and of course, then you can start confusing with Animal Farm. So, but anyway, that's what we do here. We don't speak, you know, we don't talk of public variables, public instance variables. That's banned from our language. Okay, so we don't have certain thoughts. Okay, and that's pretty much what we're doing. So, but to answer your question in a very superficial way, try-catches are not used for efficiency. Try-catches are used to catch errors, and that's one thing that Gosling made a big deal of. And sometimes, some parts of Java actually violate that, but in general, you know, that should be done only when something is erroneous. And here we expect composite nodes. We expect leaf nodes. So when something expected happens, we don't try to deal with exceptions. Okay? When something expected happens, we don't deal with exceptions. Okay? So that's okay.
Do we need to define container? I mean, like, do we need to make the component a container?
So the container is provided by AWT. Okay? So where do you think, which of these nodes you think are containers?
Split pane, frame, JPanel.
So all of these are subclasses of container.
Yeah. Okay.
So we're just passing these nodes which happen to, but in our color subtree, we're not going and saying panel or frame.
Yeah, of course not. Because you don't know.
Because we don't want to know.
Yeah.
Okay, if you want to build something that's general, maybe we'll use it for this tree and maybe we'll use it for some other tree too. So we want to have a real recursive algorithm. And you can see that by typing it at a more high level, I can actually have a nice recursive method.
So what's the order of components that the big components refers to? Because you use the way this is stored, like this order.
What's the order? So how do you actually add a child to a container? I just mentioned, which method do you call?
Add something.
Add something, which is going to really be an append. So that gives you the answer.
So you have to say two. Depends on the main method, which one do you add first?
At some point, I added a split pane to frame. At some point, I added 2 panels to the split pane in some order in my code. Okay, I didn't have them added by 2 different threads. Okay, I just said in one thread, add in this order. Okay, if I did have 2 different threads, I better have had a synchronized method so that they don't interfere with each other. Okay, so that's it. Okay. Okay, so maybe you understand it, maybe you don't. Part of me says that I hope you don't understand it completely because I spent hours with this animation that I'm going to show you next. So hopefully that's going to be useful to you. So this is my recursive reduction step, which is my terminating condition, by the way.
This is if is not a container.
Okay, that's my terminating condition. Any other terminating condition?
when I is larger or equal to.
When I have no children. When I'm a container, but I just don't happen to have a child. Okay? And like I said, when you guys do recursion later, people will say, just have containers. And a leaf node is just a container with no children. Okay? And then you won't have to deal with instance of, you'll just have a little cleaner code that way. But you've now got, you've got an array stored there that you don't need. Okay? And this is not how AWT works. Okay, so these are my terminating cases. Okay? So now let's go through my animation and just understand completely what's really happening. Okay? So I am going to now call, I'm recursing. I'm going to use the word recurse as a verb. Okay? Computer scientists do this a lot. And I'm going to recurse with JFrame. So what is the step involved? I'm going to go and go to color component. Okay, that's my first step. And that's going to color it. Okay. And next I'm going to go and, so I've visited the node, which means I've processed the node. Okay. And now I'm going to go to the recursive step. Okay. And I've got only one component, one child. So I'm going to recurse on that. Okay. And once I do that, where is my program counter going to go now? I'm going to go and enter color subtree again. And I'm going to basically do this thing again. Okay. Which means I'm going to color this. Okay. And now I'm going to, so I've visited. So now tree traversal is visit all nodes in the tree. And I visited the nodes, I'm going to visit subtree now. And what we've done is a special kind of traversal. It's called preorder. I'm visiting the parent before I visit the children. I'm being a little selfish as a parent. Okay? And there are other orders too. Okay? And if this is preorder, the opposite would be, the word would be postorder, and that would mean visit the parent after visiting the children. Okay? So this is preorder traversal. Okay? And now I'm going to basically go to JSplit pane, go to its children, again enter color subtree. Okay? And now I'm again going to go to the color method here. Okay, color this. Again go to the color subtree, go to JText field. Okay? Color it, and now what happens? Okay? So if you're not careful, you see that I've got all these red boxes cascaded. These are all my calls I haven't finished. Okay? That's what happens in recursion. That you have multiple calls, and if you're not careful, those calls keep just building up in front of you. Okay? But fortunately, I have a terminating condition, so I'm going to return from I'm going to color JText field. After this, I'm going to just not go down anymore, which means I'm going to return, and I'm going to return from JPanel because it had only one child. And now where am I going to go? I'm going to go again through this loop to the next child of mine, which is JPanel. Okay? And of course now I'm going to color that, go to its children, visit that node, color it, return, and I'm done. Okay? Neat. So I told you guys before I was an engineer and I learned programming in Fortran, which had no recursion. And I thought computer science was pretty boring compared to what I was studying. And then I saw this. I thought, wow, this is so cool. Okay, so I hope you guys think so too. So remember, recursive methods should have base terminating cases, and the recursive smaller problems. And the recursive calls should converge to base cases. And we saw that, we did the recursion with something simple like factorial and something more complicated with this, like what we saw here. And in both cases, we have terminating cases and recursive reductions. Okay? So in that sense, they are united. Okay? And in the number-based recursion, method gets some number as argument, and recursion occurs in smaller or larger number, depending on where your base conditions are. Typically, it's a smaller number. and recursion ends when some number argument reaches some limit. Okay? So when we did the factorial, you know, you can imagine going from negative numbers to higher negative numbers to smaller towards 0, okay? Or we can go from positive numbers towards 0, so we can recurse on a smaller or larger number as long as we reach some limit. And tree-based recursion, same idea, okay, except that recursion occurs on the smaller subtree. Okay? So we haven't made the number smaller, we made the set of nodes you're going to visit smaller, which is what we did with list-based recursion. Okay? Okay. So I did a particular kind of morpher, which is a coloring morpher. What if I want to change this and do a magnifying morpher? Okay, as it turns out, each component has a height and width, and you can do set width and set height. Okay, and because there are layout managers, you're kind of fighting with Java when you do that. But you know, we can see what happens when we do that, when we do this. Okay, and if we had no layout manager, we'd get exactly what we want. Okay, so given that I can do a set width and I can do a get width, I could magnify a component, right? So let's say now I'm doing a different kind of visit. Okay, we've colored and now we want to do the, you know, the plumbing or do something else. Okay, so our other activity is now magnification. So how would this code change?
You only need to change the method definition of color.
So I need now a magnifying method here.
Yeah, you want to change the name to it, but
Yeah, I change, and what else would I change?
just the method height. Change it to change set height and set width.
Okay, I set this to set height, set and set width.
Yeah.
Okay, and then I go and do a global substitution. Change this color to magnify, magnify, magnify. Okay. So here's the visit I'm going to do. Okay, it's going to be different, and because of that, I'm going to have to change some other code. Okay. So this is my magnifying morpher, and indeed I've got a different thing here, and I'm just going to change, yeah, exactly what you saw. Okay. And dimension is just object, it is a pair of numbers. And what else did I do? I change this and I change this. Okay. And I can have another kind of traversal. Okay, I'm just showing you that this traversal is something you can do a lot of. Okay. This is an animated magnification, which will actually show us things happening in the user interface. Okay. So it magnifies and then it goes and sleeps for a while. Okay. And this is actually, I think, a video. So we can go and see what happens. So what should happen? We'll see what happens is a little confusing. But if I go and animate this right now, what do you think should happen here?
First the frame expands.
First the frame expands, then maybe the split bar expands.
Yeah.
This, okay. And then the panels expand, and then the buttons expand.
First one panel and its component, and then the other panel.
Then its component, right? So hopefully we can see this in the animation. Okay. Except that we use a layout manager, a row column manager, and that's going to not like what we're doing very much. And so let's go and see. Let's see if I can play this video. Or is it? No? Okay. I guess I can play the other videos I have here. I have to update my PowerPoint version. It's doing things? Oh, good.
It didn't actually.
So the top level frame, like I said, there are a lot of things happening here. I'll show you another a cleaner one later, okay, which has got no layout manager. But you saw that things were kind of happening almost as I said. Okay. The execution happened exactly as I said, but it's just that certain things didn't. Okay. Now, and this is what I'm going to use now. Okay. This is the one. Remember, we created when I showed the composite pattern. I created these rectangles within rectangles. Then I created a similar object with swing. Okay. And here, this was the text field, and these were all panels. and I drew borders around these panels to make these rectangles. Okay? So my structure is this: J panel, J panel, J panel, J text field. And how did I, and so this is just the code which we saw earlier. And the interesting thing is that I've set the layout to null. So now I'm no longer fighting the layout manager. Let's set the rig. And now I'm going to just go and call, I'm going to use the same subtree traverser on a different frame. And because I did not bound it to any particular type, I just said contain component, and I would do an instance of to check if it's a container or not. And I never check for panel or split pane. I can just use the same to do that. And let's go and see whether I can play this at least. See whether I have any animation. So I should go first to the frame. Okay, so first the frame size should increase, then the panel size, then the containing panel, and so forth. Okay, and let's see what happens. Okay, so now you can believe me, okay, that it's really doing the. Okay, and now what if I want to do a post-order traversal? Okay, which means I visit the root at the end, and in general, I visit the parent after visiting the children. Sorry?
Just put the magnify method to verify.
Okay, so we want a different order, and so this is going to be my order. First the text field, then the panel, then the panel, then the panel, then the frame. Okay, and see whether I can play this now. Okay, so the frame. Okay, okay. So you see now visually the effect. The end result is the same, but visually you see something. And how did I do this coding? I did exactly what you guys suggested. That okay. So here in the pre-order, you visit node before traversing children, and in post-order, you visit node after traversing children. Yeah, Marie.
What would happen if you wanted the inside one to be twice as big as the one that's around it?
What do you mean? Inside what?
The text field to be twice as big as the component that's in the text field.
So you don't want to do the same thing to each node. That's what you're saying, right?
Or are you just saying
No.
No, he's
I'm
trying to
saying
decide the size of the one node, depending on the size of another.
Okay.
Like the
So you don't want to just magnify a node. You want to go and change its magnification based on its parent size. So you want to set the child size to be the parent size. Is that what you're saying?
Larger than the parent size.
Okay.
Well,
So
then just spoke up later. So where?
But how do you look at components because you can't have things that are outside?
Just change the value.
okay.
As you can.
Okay, you can always set the size to be anything. Okay, it's just that what is displayed outside your parent area is clipped. Okay. So this is not meant to be about toolkits. This is meant to be about recursion. Okay, but those are all interesting details. Okay. Okay. So we've seen pre-order, we've seen post-order, and now when you go to data structure class, okay, and you guys are bored when the professor teaches it, you can all blame me for it. Okay? But again, I didn't mean to really take things away from that class, but we'll see that there's something I'm converging towards here. Okay? So we have tree-based recursion, and we are going to visit children, and there's pre-order and post-order, and they're defined as just as I said earlier. This is just some textual description of that. And this is what I want to get into now. Okay, I want to get into the software engineering issues here, which your data structure books don't get into. So I want to see that given that we do this traversal a lot, okay, we want to do one kind of traversal where we magnify, animate, magnify, color. Marie has some other kind of magnification she wants, where the child maybe is the same size as the parent, or maybe that's not what she wants, but maybe that's something you do want. So there's just all kinds of visiting possible, all kinds of traversals possible. And yeah, recursion is fun to write, but you can also get it wrong. So we don't want to duplicate code in general, okay, even if it's beautiful code like recursive code. Okay. So, and have we done some reuse? So if you notice, this particular code I wrote worked for this structure and worked for this structure. That's wonderful. Something good we did. Okay? And that good was that we didn't tie this to panels, containers, split panes. We said we don't need to worry about that. We just need to know what the parent is, what the children are. And so we only need to be bound to the types, component, and container. Okay? So we use the same traversal and visitor for two different trees, just because we typed these arguments to this method properly. Okay? Now we did something else. We made the visitor method separate from the traversal method. Okay? Did that buy us anything? In general, when we separate things, we can do more reuse.
When you change the method body of the visitor thing, yeah, basically like the changing.
So when I went from magnify to animated magnify, I had to go and change the traversal too.
You don't really have to do something.
You don't have to do it if you don't change the name. Yeah, but the thing is that I want both. I want to be able to do animate magnify and magnify. Okay? And I can't call both animate magnify and magnify from the same traversal method. Okay? That's a problem we'll try to solve a little later. But I am able to do something else. So you said we couldn't keep this constant and vary the visitor method. That's a problem. Okay? But could we keep this constant and change the traversal? No? You first say no, then you give me the right answer. Okay? So he first said no, then he said pre-order for post-order. So can you guys see what did you mean by the second part?
Looks like you can change the order that you want.
Okay. Okay. So let's get this. Let me back up again. Okay. We've got two things. We've kept them separate. In general, when we make things separate, we should be able to keep one. We should be able to change one without changing the other. Okay. So we should be able to use one of these methods in context other than the other method's context. Okay. We tried with one way. We said let's try to keep this constant and vary the visitor method, and we ran into trouble. This is very much tied to the visitor method. Okay, and to understand how to do that, we need to learn a new pattern. But we did go and keep this constant and change the traversal method, because in the pre-order traversal we wrote one piece of code where animated magnify was called at the top, and in the post-order traversal we used another traversal method which called the same visitor method at a different place. Okay? So by keeping them separate, I didn't have to go and duplicate the whole code. When I wanted to do post order, I just changed the traversal method. I didn't have to go and change the visitor method. I didn't have to go and worry about sleep, magnify, and so on. Okay? So the visitor method definition is here. The traversal method definition is here. And the visitor method call is here. So they're tied to each other. But what exactly are the separation benefits? Okay, I'm sharing the visitor method with its separate traversal. So same visitor method definition I'm using, same method call I'm using, but I'm using a different traversal method where the call occurs at the end. Okay, so I was able to get this particular code shift. Okay, questions so far? Now let's go and look at the problem of. Okay, so let's go and abstract this out. Separation of concerns. This is the thing we've talked about in many contexts, model view controller and other patterns we've seen. Make two pieces of code referring to each other different if one can be used without the other. Okay, so these two pieces of code have to work together, put them in separate objects, separate methods, if one can be changed without the other. Okay, if they're not so intimately tied that if one has to change, the other has to change also. Okay? And we might want to keep the visitor method code constant and vary the traversal code, and this we can do. We might also want to keep the traversal code constant and vary the visitor code. And this we can't do right now. At least the way I did it, we had to go and do this copy and paste, where we go and did a global substitution. And it'll probably work, but you know, if you went and decided that you want some changes, you can't, you have to change everything. Okay? So what's happening is that when I go from one to the other, so basically here's where you see that there are two traversals that are more or less doing the same thing, but not quite, and I've highlighted the differences. And now the question is, can I unite these two pieces of code into one piece of code?
Something similar to command.
So you're saying, okay, so we need to somehow combine them together, okay? And we want to write one piece of code and somehow parameterize it with some object that decides how the visit should happen, okay? And we saw the same problem in the context of threads, okay? So the thread has to be able to run different pieces of code, and the different pieces of code that it ran were encapsulated into a command object. And you just pass the command object, and this guy went and called the thread object, just called the run method on the command object. Okay? Yeah.
If you had it set up to use any old command object, then you pass the type of the specific command object to
Can't use command because command has
Okay, so two things. First, you say you can use the command object, or maybe you can. He didn't quite commit himself to a command object. Okay, so we haven't quite decided. And while you were talking, he changed his mind, and he said you can't use the command object. Okay, and and you're saying if you're going to use a command object, how do we exactly use it? And let me remind you that when you use a command object, the user of the command object knows only about the run method or the execute method. They don't know what exact command has been passed. That is what the user of the command object goes and says, okay, go and run this or that. And the user is just oblivious to all of this stuff. So yes, indeed, to answer your question, if we were to use command objects, okay, who knows whether we have to or not, he has to make up his mind, and I'm giving him time while I talk to you, then we could pass different instances, and that's exactly the idea of a command object.
I meant, could we pass a command class that was then instantiated inside of the method, so then we could instantiate it for each child?
So you're saying, could we send the class, you mean like an instance of the class, or the class itself as an object?
The class itself.
As an object.
Because we only want the method, but because like for the command object.
Okay, let me just let her finish it. Okay, go ahead.
Pass the command object.
Firstly, why don't you just want to pass the command object?
We pass it because you want a separate instance for each of the children. Right?
Yeah.
Why do you want a separate instance for each of the children?
It's recursion.
Because it's recursion?
Well, because like in command objects that we use to create the subject, basically what the method is executed on, that object is specified in the command object.
Okay, so that's why you think you can't use a command object as such. Okay? What we want to do is color sometimes a root, sometimes a leaf, and so forth. Okay? So we want different actions to occur based on what node we are visiting. Okay? So either we can't quite use the command object, or we can somehow create a command object for each child. Okay? And what would we do exactly? We would get as an argument, we would get, you mean an instance of a class or the class itself?
We would get, I think, a variable that would reference the class, so then we could use the variable to instantiate.
Doesn't that seem a bit complicated though?
No,
Just create another object,
okay.
and it switch that in that object we instantiate.
And we could, but I mean, why do we have to do that?
Okay.
Yeah. Why don't, instead of, you said the reason we can't use command objects is because command objects just have a run method. We can't tell it like which components to affect. So instead of using command classes, why don't we design something similar that does let us choose which components we're affecting?
Let's say you want to take an argument in the run method and just to execute the method on that argument, not parameter.
Okay, so he says, why don't we redesign command object? And he's telling you exactly how to redesign it. That our run or execute method takes as an argument the object on which we want to work. Okay, and so we still have maybe one object. It's still recursion. It's one object. That object takes as an argument what we want to run. Okay, so here's the issue. We want to go and do the sum action like color on every node in the tree. Okay. And we want to not be tied to color or magnify or something like that. So the actual code that's executed must be decided by some parameter. We know that we can pass code as parameter essentially through a command object. That has a run method in it. And we don't quite call that. So we'll go and call an execute method with some argument. Okay, and you guys went a little too quickly. So the question is, do we have to re-implement the constant code in Traversal for each kind of visitor? The answer obviously has to be no. And before we go to that, let me go and give you the simpler solution that you all should be able to understand. And then we'll try to go to their more complicated solution. So I'm just going to have multiple options in my visit. Okay? And I'm going to have in my traversal order, okay, and this is just slow steps towards what they said. Okay? And I'm going to say, if it's magnify, I'm going to call magnify. If it's animated magnify, I'm going to call animated magnify, and so forth. And everything else is constant. Okay? So before we do all these complicated instantiating of classes, changing the command object, what's wrong with, and this is how I'm going to call it. I'm going to just go and then say traversal order root visitor option dot color. Okay? And it goes and executes the color code. Okay? So I've written one traverser that works for multiple visitors, and this traverser goes and just looks at the option and does what you want. And in our particular case, we have three choices: magnify, animated magnify, color, and I've solved them. So what's wrong with this?
It's ugly. It takes up way too much room, and you have to add in extra things whenever you want. Add another thing.
Okay, so you know, ugliness is in the eyes of the beholder, and we don't quite know that. It's certainly a lot of lines of code. Okay, but who knows how many lines of code we'll have to write with this other technique you're talking about. But the third one, now I believe that. And what's that? Supposing I want to go and do an animated color, and that's something we hadn't decided on when we wrote this traverser. I have to go and change this code. Okay? So in general, when you're doing object-oriented programming, if you've got switch statements, often they are a sign that you did something wrong. Okay? Because the switch statements have to be changed whenever a new option has to be added. And we don't want to change. We want to add new options by just creating new classes that implement existing interfaces rather than by doing something like this. Okay? So must change traverser or write new one for the unanticipated list. Okay? And now let's go and try to understand whether what we knew already works or not. Okay? So we know about action objects. These are methods. And they take as argument target object and parameters. Okay? And you can invoke the same method on different objects with different parameters. That's something we know how to do. We kind of know how to do. I told you this exists, and we saw an example of this, but this is what you get with reflection. Okay? This is what functional programming deals a lot with. Okay? And we've got command objects that just take a run or execute method, and in the constructor we pass the target object and parameters. Okay? And what we now need is an object that allows the same method to be executed with the same parameters. Okay, whether it's the same magnification, it's the same color. The same method with the same parameters to be executed on different nodes of a tree. That's what we want. Okay? Our action object, does it serve that purpose?
Well, you can better use it.
We can use it, but what was the problem, if you guys remember? Why did we go to command objects in the first place? Why didn't we just use action objects and threads? On Wednesday, you're going to know this very well. Okay? When you all looked at the notes and studied this, but this is answered very explicitly. That's why exams are wonderful. Okay? But the reason was that you can make a mistake in reflection that you can pass this wrong object and wrong parameters to a method at runtime. Okay? You can get exceptions. So that's the kind of thing we were trying to avoid. Because the action object takes arbitrary object and arbitrary parameters, and so we don't, at least the way it's defined in Java. Okay? So we can't quite use that. So what we want, that's why we went to the command object in the first place. So what we want to do is take out the parameters choice from an action object and add the target object choice to the execute method. Okay? So need an object that adds parameters to the action object and subtracts target object from command object. And what kind of object might you call this?
Visitor object?
Okay. So it's being used to visit different nodes in a tree. Okay? And it's going to take and execute the target object as an argument. And its constructor will take just the parameters and not take the target object and parameters. Okay? That's our visitor object. It's a very extremely powerful paradigm. And not many people know about this or use it. So, you know, and even when you know it, you sometimes forget to use it. But this is an extremely quote unquote beautiful way of doing recursion. Okay? So executing command takes no parameters, action takes target object parameters, and visitor takes just a target object. Okay? So and this is how the constructor changes. Okay? So both the execute methods and the constructors change when we go to the visitor object. Okay? All right?
So we're passing the visitor a command object.
Sorry, the visitor is an alternative to a command object.
Okay.
The visitor is a command object that takes as an extra argument in its execute the target object. And as a result, in its constructor, it takes one less argument. In its execute, it takes one more argument. In its constructor, it takes one less argument.
Okay.
Because ultimately, we do need all three things.
Yeah.
The question is, what is bound? What remains constant as we go from node to node? Okay? And as we go from node to node, the parameters remain the same, color. But what we are invoking the color method on changes.
So it'll start a new thread at every node.
Thread, and there's no threads here.
Okay.
Command objects can be used for threads or not for threads. So we are just going and doing the same method recursively. We went all the way down. Every method was waiting for the previous method to finish. And then we went back. Okay? You start doing threads with all of this stuff and things become even more interesting. Okay? But we're not doing threads. Okay? But you might have two traversals being done on a tree at the same time. And this happens in your ordinary life a lot. You know, when you have hierarchical structures in the web somewhere, some site you've gone to and people are actually, why go to that example? Let's say we've written a paper and two people are trying to edit at the same time. Basically, we are visiting the same structure at the same time. So we get into all kinds of concurrency issues, which is not the subject. Okay? Question? Okay. So it provides an execute operation to perform some embedded operation. And it's called, and the method is not called execute actually, it's called by convention visit. Okay. And here's our example. I've got now a component visitor. It's got visit method that takes a component as an argument. Okay. That's the interface. We haven't seen the class as yet. That class will come later. But my traverser is sorry, this is the class, I'm sorry. So this is the interface and here's the class. And the class takes as an argument the magnification in its constructor. That is stores it here. And when the visit is called, it goes and does the magnification using this parameter on the node that's passed to it. Okay? So this is I went from visit method to an interface and a class. You know, it's not clear to me that I've written less code than I wrote in the case of the switch statement, but it certainly allows more extensively. Okay? So this is my component visitor interface and a specific implementation of the visitor. Okay? Questions on this? And here's my component colorer. Implement the same interface, takes a different argument, the color, it takes a different argument in the constructor, which is now a color, and it just says, uses that parameter when it on the component that's passed. Okay, so here it's just setting the color. Okay. And here's where I use the visitor. This one is totally oblivious to what kind of visitor was passed to it. It just says visit component. Okay, who knows what that visit means? That is what the visitor decided. And it goes and just passes the same visitor it got to the traverse method on the subtree. Okay? So the same object is being passed. We aren't passing classes as parameters. Who knows what that really means? We aren't instantiating these classes. We're just taking the same object and making it work on different objects. Okay? So you understand this, you really understand recursion. So, in general, what's a pattern? So, I have in this case a component tree. In general, I will have what kind of tree? Let's try to figure out the general pattern that this. We've seen a particular use of visitor, and we're going to use this visitor in different problems. So, in this problem, we have a tree of components. In general, we'll have a tree of some node types. Node types, okay? There will be some type T. We didn't make the visitor method take as an argument an object, okay? So we're going to have a tree with some node type, and in this case, it's component, okay? In this case, we have a component visitor that implements a visit method that takes as an argument the type component. In general, we're going to have a visit method that takes as the type, okay? The node type as argument. We have a traverse method that calls the traverse preorder method that uses that particular component type. So it takes it knows about this tree, it knows about the visitor. Okay, so the traverser caller of the visitor method is oblivious to its implementation. What it does know about is the tree that it's going to work on and the visit method interface. Okay? And we could have multiple such traversers, and then you can have various kinds of implementations of the visitor interface. Okay? And finally, this all has to be put together. The traverser method says, you give me a visitor, I'll visit every node in the tree. Okay? Somebody has to go and commit to the visitor at some point. Okay? And that's going to be the caller of the traverser, and we'll just call it the client. Okay? It chooses the visitor object passed to a traverser. Chooses the traverser, chooses the exact implementation, and passes it to the traverser. And that's what we have in general. Okay? So this is describing this more generally. Node type, node visitor 1, node visitor 2, traversal 1, traversal 2. There's many kinds of traversals you can have. There's in order, pre-order, post-order. Here we haven't done in order. So there's a whole bunch. Okay? Questions? You understand this, you can understand anything. Okay.
Are we going to talk about generic types?
Are we going to talk about generic types? Let's go and look at these examples. But I do have generic types. Is that what you want me to teach next?
Just like it's like related.
It's related?
Decide the node type. That's the node type.
Okay.
You can let the user.
My next topic was generic types, so you know, one way or the other, you got it right. Yeah.
Is there a way to, is there a way to error check for this? To check and ensure that the client is putting in a visitor that matches his node? Or a visitor that
So can you go wrong in the client?
yeah.
How can you go wrong?
Put in a visitor that takes different parameters from the node.
So supposing that there's a visitor that visits components, can you give it a visitor that visits shapes? The interface is bound in the traverser. Remember, for each node type, you're going to have a different visitor interface.
Yeah.
So I can't pass to a traverser that expects a component visitor. I cannot pass to it a shape visitor.
It's going to complain when in a traversal you're going to call execute with a certain interface as a parameter.
Is it going to complain at compile time or runtime? At compile time, you just can't pass the wrong type. So we are fine. This is not the same problem as in reflection. Okay? And visiting, happens a lot. So you have, when you have a program, if you see Eclipse, there's a lot of things going on in Eclipse, right? And one person it was not all built into one piece of code. Okay? You can build in your own ways to pretty print things. Pretty print, is that a term you guys have heard before? What do you think it means? Okay, formatting it. So you go and write ugly code, which means ugly meaning not the right indentation and so forth. And then you say, please go and format it nicely for me. So formatting is what they call it in Eclipse. Conventional, terms, where I'm showing my age here, is pretty print. Okay, so you can have something that pretty prints one way or pretty prints another way. Okay, and that's not bound in the tree that you built. Okay, so you have a parser. It's going to build a tree, and you can have different ways of displaying it. You want to refactor things. Okay, so you guys haven't seen that, but you can actually change the name of you can add interfaces to classes after you've written your code. Okay, there's all kinds of refactoring you can do, and you can have different pieces of code that basically visit the tree of all your components, of your program components, and do the stuff. And when you go and add new classes, again, you're basically visiting certain portions of your when you go and change things, you're visiting certain portions of your project. And that's, again, all done. I don't know if it's done by visitors or not, but it can be done, and it's often done by visitors.
I was just wondering, is there like a single button in Eclipse that you can click on it and it's going to format everything?
Yes.
There is?
There's a way to say Control-Shift-F. Is that it? Control-Shift-F is going to format. Okay.
You can even change the way it formats.
So and by the way, if something is not, you might. How many of you use Control-Shift-O?
Open.
So I think it's O. My fingers know better than mine does. But if you name a class and you don't remember where it comes from, just do Control-Shift-O. It'll import the right thing, import the right package for the class. Okay. So it'll and if there's more than one package that has a class in it, then it'll give you a choice. Okay.
Control-Shift-I automatically indents, right? Fixes all the indentation.
Control-Shift-F will format it. Who knows what I does. Okay, but at one time I told you guys, use Piazza to go and mention neat things you learned about Eclipse, but nobody took this up. But if you had, you would all be knowing these.
About it's on Piazza, but it shows all this work stuff.
Oh, you did post that? Okay, sorry, I take that back. I better go and find that.
Yeah, it's basically there's one for Mac and there's one for Windows.
Okay.
It shows you full resolution.
Okay. Please go look at that. Okay, in your future assignments at least. You're done with this class. Okay. And object editor has visitors for lots of things. So you create first an object tree, then there's a visitor that goes and attaches widgets to them. Okay. And you can write your own visitor that does something different. When listeners have to be attached to objects, that's done through visitors. Okay. And you can actually pretty print an object tree. Okay. And that's done through a visitor. So there's lots of visitors, but I think 20, 30 visitors that I have. Okay. And this is just saying so that you can read this stuff. Okay, we have variable, but let's go and see this. We said object.get class.get methods. One of those methods would be a getWeight method. We printed out all the properties of an object. We wrote this generic code to print out all the properties. Okay, and we went and got the method, we said invoke on it, we gave it the object, BMI, specific, the particular BMI object on which we wanted to do a get BMI. And we get the arguments of that, which is null. That was an action object. It was something when I presented, it was not the hard ones. Okay? And that's what object editor does, remember? It uses reflection to go and call the methods. So an action object is associated with some embedded operation. So this getWeight method is an object that's associated with the getWeight method in the class BMI. Okay, so this object has got inside it an embedded operation which it calls. And every time you want to call that an operation, you say execute, which is, you could call it execute, you could call it invoke, but there is some operation you invoke on it, where you give the target object and the parameters, and say go and invoke the embedded operation on the target object with these parameters. Okay? That is your action. Okay? So the details are that you provide an execute method to perform some embedded operation, takes the object as an argument, and the command object was like the animate command, or was like the setWeight command, and we just say setWeight.execute. Okay? Which means the command object was embedded operation plus target plus parameters. All of these things are passed to the constructor. Okay? It took no argument. The constructor took the target object and the parameters. It was burnt in. And you just said execute, execute, execute. Each time you want to redo the method, you say execute, execute, execute. Okay? So if an action object is purely an embedded operation, a command object is an embedded operation plus target plus parameters, what is a visitor object? The visitor object provides a method that is that
Or no, executed on. Like, do we define it to mean that it doesn't choose it anywhere?
it could do anything. It visits and it could create whatever habit you wanted to create. So that is.
Well, I was just saying there what there is in the embedded operation is that
Yeah, it can do anything. So in our example, it was a check method, but it could be any method with a void which could go and do anything.
So, embedded operation plus the collection plus.
Well, no, the collection was implicit in how it was called. But the check method didn't have a collection built into it, right? The check method took as an argument an element of the collection. And what did it do with that? So how was that method used then? What was the argument of the check method? Get hero, which was actually an object on which you invoked it. Invoke the embedded operation. You go and say equals. So if you remember the inequality checker, you said element dot equals the something else. So basically, and what happened with the parameters? We needed parameter. The parameters are passed as constructor arguments. So basically, a command. So in command object, the constructor takes target and parameters, and action object takes no parameters, and visitor object takes parameters as well. That's the way to look at it. That you're visiting each element is really the target object of the embedded operation. And an execute in command takes no parameters, action takes target object and parameters, and a visitor takes just target object. Okay? So in command object, the constructor takes target and parameters, and action object takes no parameters, and visitor object takes parameters as well. That's the way to look at it. That you're visiting each element is really the target object of the embedded operation. And an execute in command takes no parameters, action takes target object and parameters, and a visitor takes just target object. see what happens. We'll just have an execute method. Okay? And all command objects so this is sort of, you can imagine this to be defined in an interface. Okay? And all command objects will implement this execute method. But each command object will do different things based on what the action and target parameters are. Okay? Target and parameters are. And so that information will be given into each class that implements this interface as a constructor. So the constructor is something that will be different for each action, each command object. And the constructor can make sure that the integrity is right. Okay? And for each sentence that I'm memorizing when I go to this other country, I have a separate class. Okay? Which I memorize, and then it just blurts that out. And for each of these, I just go and have one thing blurt out. Okay? So that's the constructor that we have, which goes and ties the action. So a command object is an action object with target object and parameters, okay, which are passed to the constructor, the constructor has types in it, so the constructor will make sure that the things match. Okay? And so that's what we're going to do. So it provides an execute operation to perform some action. The execute operation takes no arguments. It's the constructor that takes arguments. Each command object will have a different constructor. Each command class will have a different constructor. All command classes will implement the execute method in an interface. Okay? Whereas an action, on the other hand, is a much more flexible thing. It can be executed on many different arguments through its execute method. Okay? So command objects is also, command objects that take, when you pass command objects, you're also creating essentially second or higher order functions. It's just that there's more type checking. Okay? And anybody who used threads, can you finally relate what you did to what I'm saying? What was the execute method called? Run. Okay? Okay, but before I go to that, this is the analogy I was talking about. If I just say do, that's a verb. You have to go and compose this correctly. Okay? Whereas command object is do plus the target, Bob, plus parameters, your homework. Okay? So that's the analogy. Do and here. Okay? And in your project, if a token is an action, what is a command object there? You have tokens like say, move. So those are like your actions. What's your command object there? The avatar is an argument to this. So you were dealing, so in one assignment you were recognizing tokens. There you were sort of doing action objects, essentially. And then in the interpreter you were doing full command. So in fact, in your next assignment, I'm going to say from a user command, create a command object. Okay? Or just create a command object you can create a command object without parsing, and then execute that command object to do some action. Okay? And that will be useful because then we'll create commands that are composed of commands, a list of commands, and a list of commands will be executed by executing each command in the list. Or we can have looping commands, okay, which will go and take some component command and loop through that command. Okay, so now your parser will not go and just do the action directly. Your parsing routines will first create a command object and then they'll go and execute the command. Marie?
Say, for example.
Say.
The command say.
Yeah.
When we change them, like what you're saying, where will the string that say is supposed to say go?
It'll all remain the same. Okay, you had tokens. You had a string called say that got converted into a command token called say. But that's an action. That represents an action object intuitively. Then what did you do? You took your tokens and composed them together into a command, and that was what your command interpreter did. And what it do was parse the tokens. What your scanner did was scan the characters to create tokens. It built a stream of tokens. From that, this parser went and created commands. So the parser had some code that went and said, if the first token is say, and the next token is Dorothy or thing, and the third token is this, then I will go and invoke the same method on avatar with the arguments. Okay? Now what you'll do is say, I don't exactly know, I won't do this directly. I will create a command object to which I'll pass the say, which will be a say command object, to which I'll pass Dorothy, some indicator of Dorothy and the arguments. And then I'll go and execute that command object to go and that execute call will go and invoke the say method on Dorothy. So this is an indirect way of doing things. And computer science and object-oriented programming is a lot about doing things indirectly. Okay. I'll try to spell this out a little better when I write this out. Okay? Okay. So we've got our command objects, okay? And like we saw, these command objects are what essentially